Hello students. So today we are going to learn regarding the electron transfer mechanism. Okay. So what is this electron transfer mechanism? In most of the coordination compounds, we see that the electron transfer will take place with the help of exchange of ligands. Okay. The help of exchange of ligands. Like this. Okay. But these are very slow. So they are very slow reactions. Okay. And what about this here electron transfer mechanism? The electron transfer is fast. So here it is fast. So how many types are there regarding this electron transfer mechanism? There are two types. What are they? One is outer electron transfer, okay, and one more is inner electron transfer. Outer electron transfer and inner electron transfer. So what is outer electron transfer? Whenever any coordination species or ion here, so if I take here one ion here like this, okay, plus 2, so like this. So whenever this remains intact, okay, so there is no change of the ligands, exchange of the ligands here. So this complex ion is inert in nature. So if I take this and if I take this another here like this plus 3, so what will happen here? So both are inert in nature. This also inert, this also inert. See here, okay, and they are saturated. These two complexes are inert and these two complex ions are saturated. Is it? And they both are saturated. So both are saturated. So during this, what will happen now? So okay, so you are not seeing, so I will write here. So these two complex ions are inert. These two complex ions are inert and they are saturated. They are saturated. So the electron transfer here, whatever takes place here, so it will take place through via outer electron transfer mechanism. So here they will go to outer electron transfer mechanism. So here whatever the transition state is formed here, whenever they react here, so they will be inert in nature. Okay, so they will be inert in nature. So there is no bridging here, and that's why. So here directly electron transfer no doubt. So I can write here CO NH3 6 times plus 3 plus CO NH3 6 times plus 2 Cl. So that is the electron transfer here from plus 2. Here it is plus 3 plus 3 plus 2. But this electron transfer is very slow. Why it is very slow? Because the complex here, so cobalt here and this the complex ion both are inert in nature and they are very saturated. Okay, one thing. And second thing you can see here that the electron transfer here. So here cobalt 3 you take one of the species. So this act as a reductant, okay, and this act as a oxidant. This acts as a oxidant. Okay. So here why the reaction is slow here? Because see here there is no bridging acid. Whatever the electron present on the nitrogen here, so they are going to form the bond here. Is it right? So that's why there is no as such ligand here capable of forming the bridge here between these here. And moreover, you can see here cobalt 3. So cobalt 3 and cobalt 2. If you see what is this cobalt, which this one cobalt 2 if I take here, okay, oxidant of the oxidant here, reductant here, cobalt 2. That means D7 system. So D7 means D7 system. So if I share the electrons here, so what will happen here? So T2G Eg, T2G Eg. So 1, 2, 3, 4, 5, 6. You can see here. Is it right? So there the electron is in Eg orbital. So this electron in Eg orbital is now very difficult now to go for the bond formation. Why? Because these electrons are used in formation of metal ligand bonds here. So Eg orbital, if the electron is present in Eg orbital, so you can see that so they are very slow reactions. Okay, because why? The electrons are present in Eg orbital is very difficult for the electron transfer here because they are utilized in metal ligand bonds. See, this is a reason. One reason why I can say the reaction of the outer transfer is very slow here. One thing, okay. And the second reason, if I go for the second reason, you can see here. So the electron is the Eg level, okay, so that is one, so it should not be there in the Eg level. Eg level is there, this is slow, the reaction electron transfer is very slow. Second second thing is the ligand. So they are not having any bridging property here. So they are not a good pi acceptor or donor here. So that's why they are not a pi type of ligand, and that's why that is the second reason the reaction is little bit slow in this. And third, I can say the reason is between the cobalt and nitrogen bond distance. Okay, cobalt and nitrogen bond distance. Okay, so it is very large. So they are unequal. So they are not equal. So cobalt and the nitrogen bond equal are not equal here. This is the main problem here. Is it right? So if you see cobalt and nitrogen bond order of this complex oxygen to the reductant, it is not equal, and it takes high energy now. It takes high activation energy EA to excite this electron or the exciting of this electron and make the bond equal. It takes very high energy, and that's why this is the reason why this reaction is very slow, and it proceeds through outer electron configuration, outer electron transfer mechanism here. Okay, so bond distance is unequal of these two complexes, and it requires high energy. So that is what activation energy to excite the ions and to make the bond length equal of cobalt and nitrogen. So that is one reason why the electron transfer is very slow in this, and it proceeds through via outer electron configurations. Is it right? And third is spin multiplicity. If you see the spin multiplicity, okay, the spin multiplicity or spin order here of the cobalt, both these is different. Of this cobalt 2, okay, spin multiplicity is different from cobalt 3. The spin multiplicity is different here. That also makes the reaction very slow. So these are the reasons why the outer electron transfer of this example I am telling you, that is cobalt hexaamine +2 to hexaamine cobalt +3, is slow in nature. Is it right? So one more example is that if I ask you how is the electron transfer in this now. Okay, so electron transfer in this reaction, Fe CN6 4 minus plus Fe CN6 3 minus giving you Fe CN6 3 minus, okay, Fe CN6 3 minus plus Fe CN6 4 minus. If you see these reactions, so how it is, which type of reaction is this? So this reaction is also proceeds. This reaction also proceeds via what? Outer electron transfer. So this also is outer electron transfer. See, is it right? But how is the reaction? This reaction is slow. Outer electron transfer, but this is slow. Okay, we have seen the results here. We have seen the different factors here. How is this reaction? So this reaction is fast. See, this reaction is fast, but this reaction is fast. Outer electron transfer only, but reaction is very fast. Why this reaction is fast? So now can you tell me why this reaction is fast? So you have to tell all the properties opposite of this previous example. Okay, so here the distance, the bond distance between iron and carbon is same. This is first point is here, the iron to carbon bond distance is same. See, this is one factor which this reaction is fast. Okay, though it is proceeding through outer sphere, outer electron transfer. Second thing is what? Now you see electron Fe. So Fe is in d5 state. Okay, d6 s2 state. If I remove 3 electrons, it becomes a d5 state. Okay, if I remove 3 electrons, it becomes a d5 state. Now if you tell here like this, so 1, 2, 3, 4, 5. So like this. Why it is down I am moving? Because this is a strong ligand. So cyanide is a strong ligand, so I have to pair in this way. Like in previous example, it is a weak ligand, so I lifted that electron to the Eg level. But here what happens now? The electron is in T2G level. Here, no Eg level. That's why easily the this T2G electron is there. So in Eg, it is the electrons are not required, not be utilized for formation of Ml bond here. See, like so that's why this also reason makes the reaction from outer electron transfer faster. Okay, and third point is what here? Cyanide. So which type of cyanide ligand is? It's a pi acceptor ligand. Okay, so it's very good pi acceptor. So it forms a very good pi bond with the metal ion, and that also facilitates for what? For fast reaction. So cyanide, so pi property, pi accepting property of the ligand also is very much important for fastening of the reaction. So that's why. So this is one the reason why the cyanide why the reaction, though it is in outer electron transfer, is taking fast. Okay. So one more reaction. So this is what. So one more point we can say here that iron here is both in same spin multiplicity. You see here. So iron 2 as well as iron 3. So both are having same spin multiplicity. So that is the third reason of this reason why this reaction. So though it is outer sphere mechanism, so it is undergoing very fast. So this is how, so today we have learned regarding the outer electron transfer mechanism with two beautiful examples, that is of hexaamine cobalt +2 and +3, as well as hexacyanoferrate +2 and +3. So here I hope that you have understood the outer electron transfer mechanism and how they proceed. In the next class, so in the next class we will take some more examples, and we will learn how that outer electron transfer. One or two examples we will take more to learn more of this outer electron transfer. Hope you understood this concept in today's class. Thank you very much.